Hello, chemistry students. This is Dr. Kirschner. This is a lecture for, trying to think. It is the lecture for Wednesday and Thursday of this week, and I'm gone. So you're listening to this recording. And by the way, it's a lecture I'm giving, but off campus, I will make it such that you don't have to do a quiz on it. We'll combine quizzes next week for this lecture plus the next lecture. Some of you will get lecture 4, and so we'll have a quiz over lectures 3 and 4 when you come back on Tuesday. The rest of you will get lecture 4 from me on the next Monday. Anyway, no immediate quiz on lecture 3. So let's go through lecture 3, which is mainly conceptual, not a lot of math, but also some interesting concepts though. So let me get right to it. By the way, at the same time, you're taking a quiz on different types of reactions, and I'm sure Miss Metaliano has gone through some of these with you, and you've taken that quiz, and hopefully you feel pretty good about it. So let me get to the topic at hand. Let's see here. There we go. Okay. So of course we're in the Unit 8 on chemical reactions. And we've talked about how to balance them, how to write them out when we're given a statement, and how to balance them, of course, was quiz 1. Types of reactions was quiz 2. And now we're going to number 3. Okay, so you've had a little bit about this, so let me go to where we are in the things. So now what we're doing today is a very, very, very brief overview of 2 things about chemical reactions. One is, what affects how fast the reaction goes? By the way, we could spend weeks on this. And then the second thing is, how do we know how far the reaction will go to completion when we know that what I'll tell you today is a reverse reaction can happen as well? We call how far the reaction will go right or left, we call that chemical equilibrium. We don't have this in the standards in the state of Ohio, and we don't have time to go through it in a lot of detail. It also involves some ugly math a little bit, but the concepts are pretty easy. But we need some of these concepts in order to do acid basis and some other stuff we're going to do later in the semester. So anyway, we're going to do rates of reactions first, and I'll show you along the way what we're doing. We'll go right to the homework on it. So how do chemical reactions occur? So what we wrote out is, for instance, 2 H2s reacts with 1 O2 to produce 2 H2Os. How in the world did these atoms come apart to rebond this way? Do they just spontaneously do that? That H2 is floating around and then all of a sudden just becomes cut in half, and the O2 too, and then they just end up coming together? Or do they have to be in the same test tube, don't they? Why do they have to be in the same test tube? Why do they have to be around each other? Well, it turns out the way chemical reactions happen is that these guys actually collide with each other. And those collisions, depending upon if they're the right collisions and they have enough energy, and might actually break the bonds. Now the question is, when the bonds are broken, is there any reason they would want to bond differently than they did before? And sometimes there is, not all the time. So I don't want to imply that all chemicals, when they collide with other chemicals, are going to react. If they can react, depends upon a lot of things we can't get into. So anyway, the bonds of the reactants must be broken, and the bonds have to be made. For either of this to happen, something has to make the bonds break. That is collisions. Okay, so this has something to do with rate, by the way. If we're going to increase the collisions and the energy of the collisions, we can make things go faster. So here we go. So I'm going to make this a little bit bigger. All right, so here are the reactants. And reactants are green, products are red, I guess. And we're seeing these guys are colliding. So reactants molecules must collide with 2 things. Enough energy, because it takes some energy to break bonds between atoms, and a lot of times you have to hit in a certain location. So some of these collisions will not work because they're just not going fast enough. By the way, think about what makes molecules go fast. You probably heard of it last year as kinetic energy, which means temperature. Okay, not enough energy. What I should put number 2 is not the correct orientation. Okay, so an analogy for reactions to work is this. Because they have to collide, it's almost like you have to input a little bit of energy before they break bonds and then make new bonds. And sometimes the new energy they have, the new potential energy, is actually lower than what you started with. But even when it's lower, you might have learned last year that everything tries to become more stable and have less potential energy. To do this, instead of thinking of it as you're on the top of a hill and you just slightly push yourself, in chemistry you have to actually push yourself over a little hump before you go downhill. Anyway, so for a reaction to work, reactants must collide so bonds are broken. But when they come close to each other, it's very, very unstable. So a lot of times you have to have some input of energy. So the potential energy goes up when reactants get close, and that's because they're outer shell electrons, which hate each other. Remember, electrons repel each other, are less stable. Hence, what affects the rate is whether reactants move and hit each other with enough energy. They can do that in a couple ways, so let me write down a couple of these things. Ways to increase the rate of reaction. Well, increase how crowded it is. Just put a ton of reactant in it. Just like you put a ton of dynamite, gives you a bigger reaction. Same thing here with the number of reactant molecules. Increase the temperature. You might have noticed that you can get reactions to go if you heat them. And then what we don't see a lot is if they hit in the right orientation, but you can get both of these to have the orientation to happen with these two. Or in your body, you can have what are called catalysts or enzymes that do this for you and increase the rate a billionfold sometimes. So here are some things to know as far as concepts. How do you increase the rate of reaction? Let me go through it first. Catalysts. They do it without increasing the temperature or the amounts of reactants. Increase the amount of how crowded it is. We call that concentration, how many of things there are in a particular area. Increase the surface area of the things that are reacting, so there's more intermixing of the molecules. Increase the temperature so they hit each other higher. And for gases, you make it more crowded, which is called increasing the pressure. So if you can kind of have your hands on that, that's kind of what I want you to get out of that. So we have that all listed up. So I wrote that all out down there. Okay, so we put a couple scenarios in here. We increase the concentration, the rate goes up, increase the temperature goes up. All of these would make it go up. Okay, the next thing we're going to do with this is we're going to talk about a thing called a rate law expression. Okay, what the heck is that? Well, they take a reaction, and then they tell you that the rate of the reaction, how fast it's going to go, is some constant times, and these brackets, notice they are chemical A and chemical B. They actually have to do with the amount or concentration of them. But they'll give you a rate law expression somehow, which we don't have time to get into how they figured it out. And then they'll ask you to interpret what happens if you do this or that to it. Now, what I want you to be careful of is this. You're going to be told what happens to A as far as amount and B. Watch out for your exponents. So for example, you're given this in a quiz problem or a test problem. What would happen to the rate, this, if the concentration of A or the amount of A is doubled? Okay, so let's say A is 1 and B is 1. You get 1 K for R. Now put in 2 for A times B, which is 1. But remember that 2 is squared. So if you double something, you're going to square the output if it's for A. So doubling will quadruple times 4 the rate. What if you take the amount of B and cut it in half? Well, this is exponent of since there's nothing there, it's to the first power. You would half the rate. Catalyst would make it go a lot quicker, but you'd have to put a number on it. Okay, second concept today. Reaction equilibrium. Okay, that has something to do with the rate, but it's kind of like a separate topic. So again, we're trying to just know that it exists, that rates depend upon concentration and temperature and stuff like that, and that's important, but we'll never really touch it again. This one we'll have to touch again with acids and bases and stuff. First thing I want you to know about reaction equilibrium is the following. Basically, all reactions are reversible. So if you take H2 plus O2 to make H2O, H2O can also break apart into H2 and O2, whatever. Forward reactions can go and so can reverse. The question is, all reactions have a sweet spot. What I mean by that is that when you put a reaction together, you'll get to a point where the amount of reactants is going to be stable and the amount of products is going to be stable. So anyway, let me put this down. Each reaction has its own equilibrium. What does that mean? a place in which the amount of reactant and product is stabilized. But what that state is it when you have 99.9% product and barely any reactant? So when you have 50% reactant and 50% product, it depends upon the reaction. All of them have a different equilibrium, a place on the seesaw where they're at the right state. So this is a state in which the proportion of reactant to product is stabilized. Not that reactant and product are equal, though. As I put down here, it does not mean that the amount of product equals reactant. So by the way, way back when we did stoichiometry and we did what we call as theoretical yield, that theoretical yield was based upon the premise that the reaction had an equilibrium in which all the reactant went away and we made all product. That might not be the case for all reactions, actually. Another way to look at this, if you look at the rate of a reaction and you start out with all reactant, you're going to get a really high rate because remember, the more reactant you have, the more crowded, the faster it is. But as the reaction goes on and the reactant is the chemicals of the reactants turn into products, it's less crowded. And all of a sudden, as you get lower and lower amounts of reactants, it gets less and less crowded, less and less collisions. And that, after a while, you're going to have a flatline rate of basically what will be its slowest. As you do the forward reaction, you start out with all reactant. You have no reverse reactant because you have no products to turn back into reactants. But as you increase the products because you're doing this forward reaction, all of a sudden this rate goes up. But then when both rates are the same, this is when you're at equilibrium. So what that means, though, it doesn't mean you have 50% product and 50% reactant. These reactions are different in the fact that even though you might say the collisions are the same, which collisions are going to result in the reaction are different, though. So anyway, here's looking at it from the perspective of how much reactants we have. Because the two rates are equal, for every time you make a reactant, you make a product when you get the reaction rates equal. But in this reaction, they're showing you that you get mostly products at the end and less reactants. This curve, by the way, they both flatline, but this could be different for each reactant. So for instance, if you did a totally different reaction, you might see that the products are down here and the reactants are up here, or that they're both about the same here. So this is just one example for one reaction in which it's favored for products. So what they do to help you calculate, okay, well, which direction is favored? You just said, Dr. Kirschner, that some reactions, you'll get almost all products and no reactants when you get to equilibrium. Some other ones you might get very little product and almost all reactant. How do you tell the person for a reaction which direction is favored? Well, they do it, of course, in a complicated way. What they do, look at this equation here. These are the reactants. These are the products. They actually take the amount of reactant, we call it concentration, we put it to the power of its coefficient, which you're like, wow. Can you imagine a 6 there? And then we multiply it by the other product. Then we put it over the reactants to their coefficient powers. They take the products. So you get this really ugly fraction. But notice here then, if you have a reaction in which you almost get all product, with very little reactant, you can't have both, by the way. You either make all your reactant product or all your product reactant. I'm just saying it favors the product. Your numerator is going to be huge and your denominator is going to be small. If the reaction favors the left, in other words, it's at equilibrium, you have mostly reactants, then you're going to favor the denominator and it's going to be small. So this leads to this conclusion. If the KEQ you're given is above 1, you can then say that that reaction favors the product. If it's below 1, which means the denominator is big, it favors the reactant. Okay. So write out the equilibrium equation for this. What you do is you take product over reactant. Let's go back to here. Take the product to its coefficient power, whatever it is, over the reactant times another reactant to its coefficient power. So we'll do that. So it'd be HI to this HI squared over H squared, H2 times I2. You can plug these guys in and get the actual value. And now given these values you get, once you calculate that in class with Ms. Battagliano, you can figure out if it's greater than 1, it favors the product. If it's less than 1, it favors the reactant. Last thing. This is what biologists use it for the most. Le Chatelier's principle. What if the reaction is at equilibrium, but you change something? You artificially take away more A, or add more A, or do this to C or whatever. It says if reactants or products are added to a reaction that is in equilibrium, then the reaction is going to shift away from that added substance to get back equilibrium. Think of it as a seesaw. If you add more C, it will say, well, wait a minute, my equilibrium constant's changed. It's now made it too high. I need to shift it this way to get rid of the C I added. If I add A, shift it away from the A. If you take away something, you will shift towards that something you took away to replenish it. So let's practice this a little bit. Well, I don't have any practice here for it. So what I need to do is go to the homework. Let's try that homework instead. Let me go to the homework. There we are. So here's one of this homework, by the way, is only one page. So if you're like, whoa, this one went over my head, just hang in there. Now, all we're doing with this is we're looking at this equation and thinking about what happens if we change the amounts of A and B. So if we change A and cut it in half, if this used to be 1 and now it's 1/2, this would be 1/2 of what it was then. If we triple B, so let's say we have a 1 and a 3 before, so it's 1 times 3 squared is 9. But now, let's make this 1 and let's make this 1. But now let's triple B. So 1 times 1 squared is 1. But now we make B 3, we have 1 times 9, so we go up 9-fold. So take your 3 times what it was before and just square it. 3 squared is 9. If A is doubled, the concentration of B is cut in half. Well, this is 2, and now this is 1/2 squared, which is 1/4, so that would be 1/2. So if you want to do that on the board, that would be great. Now these are just concept questions, thinking about collisions. If you decrease the temperature, the collisions won't happen with enough energy. Increase the pressure, that means they're colliding more often, that's good, that'll increase it. Enzymes, of course, make it go up really fast. Add more reactants, you're making more collisions. Okay, which direction would equilibrium go if you add more reactants? You try to go away from it, so you would go right and make more products. If you make more products, go left, and you can do this with Miss Italiano. And then this is one in which you write the equation out and you plug these guys in. Then you're done. So you guys can work on this with your substitute teacher and get it done, and then I'll be ready for you when you get back. Thank you so much.